Hello again, Ling 441. We're back, and today I want to talk to you about the other model of how we go from the articulation of vowels to their acoustic properties. And this is the two-tube model. So I'm going to talk about that. I'm going to talk about vowels. I'm going to talk about tubes. And I'm also going to spend a little bit of time at the end of this talking about music, just for kicks. I know there's a lot of you out there who enjoy music to a greater or lesser extent, and we can talk a little bit about the acoustics of music and how it kind of relates to how we produce vowels and speech in general. So let's get into it. Like I said, this is the second theory of vowel production, and it's known as the two-tube model. And if you do continue on with linguistics and phonetics and go out into the world and talk to phoneticians at some length about how vowels are produced, this is the model that will more often be cited by phoneticians when they're trying to explain how you get specific formant values for whatever kind of vowel you're producing. Maybe the reason for that is it's a little better mathematically defined. You can use equations to kind of derive exact values of formants for a particular articulatory configuration for a vowel. So maybe that makes it look more sophisticated or more solid. Rather than kind of making general predictions based on like the perturbation model. By the end of this lecture, they'll kind of talk about there's sort of trade-offs for the two models. One does some things better and the other does other things better, and they kind of complement each other that way. So there's reason to know both of them, but without any further ado, let's talk about what this one says. So the two-tube model holds that if you make a constriction in the vocal tract, then it kind of approximately divides the vocal tract, the whole thing, into two separate tubes. And then each of those individual tubes, which are parts of the bigger tube, each of those individual tubes has its own characteristic resonant frequencies. You can calculate what the formant values are separately for the individual tubes, and then you kind of have to put them back together to get the accurate picture of the whole once you're done. So the first resonance of one tube will produce F1. The first resonance of the other tube will produce F2, generally speaking. And when I say the first resonance, I mean the lowest frequency resonance of that tube. So I'll give you an example here. This is a two-tube model of the vowel ah. So we have a constriction here in our pharyngeal region, and we know what perturbation theory would say about that. This model, though, is going to say that this narrow constriction here is basically going to split up our tube into two tubes. So this is the back half of the vocal tract in the pharyngeal region here, and this is the front half of the vocal tract in the oral region. And these are two tubes pretty much cut off from each other, and they each have their own length. And then this is kind of like the plastic tube model we saw with the duck call vowels last time. This is kind of like a representation in three-dimensional space of what you can kind of consider these tubes to look like. This one is a narrow tube way in the back of your throat, and this is the wider tube in the front half of your vocal tract. So I'm just kind of linking those up here with the front and the back tubes there. So you can kind of there's a simplification here. We're going to do some math. It's sort of like the physics you learned in high school or whatever, that we're going to make some simplifications to get it to work. Both tubes can be considered to be closed at one end, this one at the glottis end, and this one at this constriction end, and then they're open at the other end. So it's a little bit weird that you're considering this to be both closed and open, so that's kind of a simplification you have to make to get this to work. This one's pretty clearly open here at the front, but this is supposed to be a tube closed here and then open here. So we can use the same math that we used before for the whole vocal tract to calculate the formant frequencies of schwa. Okay, so that math, as you might recall, says that the formant frequencies of an open tube of length L can be calculated with this equation. So this 2n minus 1 factor just shows you how the formant frequencies kind of go up in frequency as you go from the first resonance, where n equals 1, to the second resonance, where n equals 2, so on and so forth. C is 35,000 meters, 35,000 centimeters per second, and it's the velocity of the speed of sound, it's the speed of sound. And L is the length of the tube, and that goes here in the denominator. Okay, so all that really matters here, if we're going to do math, is what the length of these tubes are. So if you read through this a discussion of this theory in the textbook, Sorry, I got a little frog in my throat as usual. I don't know what its formant values are, but we'll figure that out later. If you read through this section in the textbook, it goes through a little discursus about, well, do we need to consider like the width of the tube when we're calculating these frequencies? And basically says yes, you could, because there are going to be resonances going this way, but this I guess would be a closed tube on both ends. And more crucially, this width is a lot shorter in length than the length of the tube this way. So these formant frequencies would, because that distance is shorter, would be much higher in frequency than these frequencies, these formants. So we're not really going to see or care about these in the spectrogram or in sort of anything having to do with the vowel. Acoustically, the formants that will be most prominent are going to be produced by the lengths of these two tubes. So let's consider the first tube, or the front tube first. So I'm going to kind of derive these with the default length for the whole vocal tract of 17.5 centimeters. And we'll say the front tube is a little bit longer than the back tube. So if this front tube is 9.5 centimeters long, we just have to do the math the same way we've done it before. So in that case, F1 is going to be 35,000 centimeters per second times 1, because n is 1 here, and divide that whole thing by 4 times L, where L equals 9.5 centimeters. And this is just crunching out the numbers either by hand or with your calculator or whatever. If you figure out what this amounts to, it's 921 hertz, more or less. We can compare that to what the corresponding first formant frequency would be for the back tube. So I said before, the whole length of the tube is going to be 17.5 centimeters. So if the front tube is 9.5 centimeters, the back tube is going to be 8 centimeters long. So in that case, the only thing we change in our calculations for the math, we're changing the length. So it goes from 9.5 to 8 centimeters. And as you might imagine, this is a slightly shorter tube, so we should expect to have slightly higher formant frequencies for it. And if you do the math for that, you wind up with an F1 of 1093 hertz, more or less. So we've got two formants. We're both labeling them as F1. So one is 921 hertz and the other is 1093 hertz. But they both come out of the mouth at the same time. They're being generated by different parts of the vocal tract. But as a listener, you're going to hear them kind of combined into one. So the lower frequency resonance will wind up being F1 in the output production of the vowel. The second lowest resonant frequency is going to be F2. So this one comes from the front tube, and this one comes from the back tube. I'm going to say this more than once in this lecture, but it doesn't matter which tube the formants are coming from. Whatever formant is lowest in frequency is going to be F1 in the output of the vowel, and whatever formant is second lowest in frequency is going to be F2. And you can kind of say, well, yeah, it does matter a bit which tube those formants are coming from, not in terms of whether that tube is front or back, but whether that tube is longer or shorter. So the longest tube is going to produce your F1 in a case like this. The second longest tube is going to produce the F2. And the second longest tube in this case, because there's only two tubes, is going to be just the shortest tube, basically. Yeah, just like the internet, your mouth is a series of tubes. Okay, so let's take a look at these actual values. See what we get. So this is Bruce Hayes saying the word HOD, which I'm going to guess you have never said before in your life outside of phonetics class. But here we go.
Hard.
Let's turn that up a little bit.
Hard.
Yeah, so this looks like a classic here. The formants basically come together through most of it, and then they split off a little bit here because we're changing the formants when we get into the consonant. So let's take a spot here in the middle, and we'll say F1 is about 740 hertz. F2 is about 1221. So we had predictions of like 920 and 1093. We don't know exactly what Bruce Hayes' vocal tract length is. I guess I could assign that for an exercise too. But these are a little bit more split apart than we might expect from each other, even though they come together in the spectrogram itself. So what's going on here? It has to do with a phenomenon known as coupling. So like I said, we have to make some assumptions to kind of make this whole thing work. And the fact that our assumptions are not exact representations of reality mean that reality is going to sneak in there anyways and sort of make our predictions a little bit off at the end of the day. And what makes our predictions off here, and in this case, is this phenomenon of acoustic coupling. So this is going back to that point where assuming that both tubes are closed at one end and open at the other is too simplistic for this vowel when it's actually produced. And that sort of connection that you get between the two tubes, that little bit of an opening between the two, leads to what is called coupling. So coupling basically means, there's kind of bleed or whatever you want to call it in terms of like the waves going resonating in the two tubes as they kind of cross over from one tube to the next. The amount of coupling you get depends on the cross-sectional area of that open end of the small tube. Basically, the larger the opening, the more acoustic coupling there is. So the larger their opening, the less the two tubes are operating independently of each other. Hopefully that's fairly intuitive. And of course, the larger the opening, the more those formant frequencies are going to start to resemble those of a uniform open tube, like we got for schwa when we first started doing this math, right? So I'll give you some examples of what this means graphically. So this is looking at the same sort of setup with slightly different variables here. So this is just length of one or length of the back tube. This is the cross-sectional area of the back tube. This is the cross-sectional area of the front tube. And this is the length of the front tube. One is back, two is front. So what this graph shows you is what happens as you change the ratio of the cross-sectional area of the back tube to the cross-sectional area of the front tube. So if basically this is again an idealization because you can't really get this to work in this sort of situation where the cross-sectional area of the back tube is 0, that would be closed off. It really wouldn't be a tube at all. But that's the assumption we're kind of making to get the math to work, basically. So in that case, our back cavity would be like 8 centimeters. That's what we calculated before. So that winds up giving you an F1 of about 920 hertz, kind of lines up over here, and then an F2 of about 1093 hertz, more or less, in this region, right? That's the ideal case. We're not dealing with this ideal case because it wouldn't actually work in reality. Instead, we have a bit of coupling. So the bigger this cross-sectional area is here, the more kind of connection there is acoustically between the two tubes, right? So there's more kind of space for the energy of the back tube to kind of escape into the front tube, and vice versa for that matter. So if you open up that back tube a bit to be 1/10 the area of the front tube, then you get a formant frequency curve that looks like this for F2 and this for F1. So as you're opening it up, this is when you open up the back tube to be even bigger, where it's 1/4 the size of the front tube. You get even more spread between your two formants. Basically, the more coupling there is, the more the formants are going to shift away from each other. And if you keep going and kind of stretch this out to its sort of limit, you would get basically A1 being equal to A2. We have that uniform tube kind of scenario we talked about before, and it would just look like a schwa, right? You just have a uniform tube of like 17.5 centimeters, and F1 would go all the way down to 500 hertz. F2 would go all the way up to 1500 hertz. That's kind of as much as you can possibly split them apart from each other. So the more you open that up, the more you're going to shift the formants away from this ideal scenario that we've been using to crunch the numbers. That is not something you're going to have to worry about when you do the math, because the math for this is too complicated for us to worry about. I just want you to know that in principle for why when you do the math, it's not turning out the way we see in a spectrogram. But hopefully that makes sense. And I'm not going to say a whole lot more about it. Okay, so I will repeat what I said before, though, which I promised you I would repeat. which is that F1 is not necessarily associated with the front tube and F2 is not necessarily associated with the back tube. Instead, the longer tube is going to determine the F1 resonant frequency, and the shorter tube is going to determine the F2 resonant frequency. And this is described or in theory explained in the textbook with this graph, which I believe is called a nomogram for some reason. I'm not clear on. What's also not super clear is exactly what it's saying. So most students, when they look at this, are like, what the heck is going on here? So the idea here is that we're plotting the back cavity length here on the horizontal axis. And then based on the back cavity length, we can know exactly what the front cavity length is, assuming a default value of 17.5 centimeters for the entire length of the tube. I can go back here and show you that this is basically the way they plotted it in this representation as well. It's the same kind of idea. The two have to trade off from each other. So if we only have two tubes and we know the value of the length of one of the tubes, we'll automatically know what the length of the other tube will be because they both have to add up to 17.5 centimeters at the end of the day. So that's all that's being plotted here in terms of the back cavity length. And then based on the back cavity length, we could calculate the values of the back cavity resonances. And then because we automatically know what the front cavity length is going to be, we could calculate the values of the front cavity resonances as well. So these lines are supposed to show you the front cavity resonances as the back cavity length changes, and these are supposed to show you the back cavity resonances. I feel like this is not the clearest representation of what's going on, so I've jazzed it up with some amazing graphics, which I'm about to show to you now. They look like this, which maybe makes things clearer. But this is basically saying that the things in blue, these lines in blue, are showing you what are basically F1, F2, and F3 for just the front cavity alone. And the lines in red are showing you what are F1, F2, and F3 for the back cavity by itself. So again, we can kind of go to our default scenario. I think this might actually have just a default value of 16 centimeters for the whole length of the tube. So let's say my back cavity length was 6, then my front cavity length would have to be 10. So think about that for a second. If my back cavity length is 6, the front cavity length is 10, which tube is going to produce lower frequency formants? The one that's longer, right? So the longer the tube is going to produce lower frequency resonances. It'll give you the F1. The shorter tube will determine the F2 resonances. So based on a back cavity length of 6, I know this is my F1 for the back cavity alone. My F2 winds up being this for the back cavity alone. F3 is going to be way up here somewhere. It doesn't fit on the graph. But F1 is going to come from the front cavity because it's longer. It's 10 centimeters. So that's why it's lower here. So this one, this is my F2 for the front cavity. This is my F3 somewhere up here for the front cavity. The thing to notice here is F1 comes from the front cavity. F2 comes from the back cavity because it's the lowest frequency resonance for the back cavity. When I get to F3, that's actually F2 for the front cavity. And I can't really tell. I picked a bad example. They're kind of tied here between F4 and F5. But generally speaking, you can expect these to kind of alternate, where you get F1 for the longest tube being F1 for the whole vowel, F1 for the other tube being F2 for the whole vowel. Then you go back to the other tube, and that second resonance for that other tube becomes F3. Second resonance for this guy becomes F4, so on and so forth. Hopefully that makes sense. But if it doesn't, I'd recommend staring at this graph for a long time until you understand it. And we can also look at the flip side, right? So if the back cavity was 10 centimeters long, the front cavity would have to be 6, and we get the exact opposite pattern in reverse, right? So the back cavity gives you F1, F3, and maybe F5. The front cavity gives you F2, so on and so forth. Same math, just flipped around for the two tubes. The two-tube model. Okay, so let's try this out. Let's think about a scenario where you have an overall vocal tract length of 17.5 centimeters. So we know if that was just operating by itself without any constrictions anywhere, the lowest resonant frequency would be 500 hertz. The second would be 1500, the third would be 2500, all the way up the scale. But we're not going to do that. We're going to make a constriction somewhere in the tube. We're actually going to make it relatively close to the front. So the length of the front tube is going to be 7 centimeters. That would mean that the length of the back tube has to be 10.5 centimeters, right? They both have to add up to 17.5. So I'll walk you through the math. Let's do the front tube first. It's shorter. We can expect its resonant frequencies to be higher for that reason. And we're just going to use this equation, which we've derived and talked about at some length. And we're going to figure out what the formant frequency should be if L is 7 centimeters, right? That's all we really need to know for this, because we've done the other stuff more than once, enough times to kind of be familiar with, right? So if the length of the front tube is 7 centimeters, and I'm looking at F1, where n equals 1, so 2 times 1 minus 1, that whole thing equals 1. I don't really have to worry about it. C is going to be 35,000 centimeters per second. Then I divide it by 4 times L, which is 7. So 35,000 divided by 4 times 7 is 35,000 divided by 28. If you want to crunch through the numbers by hand or with a calculator, you wind up with an F1 of 1250 hertz. Yeah, I'll just say this again in case I wind up reusing these lecture notes for whatever reason, but if we have an in-person final exam for whatever reason in the hopeful future, you can bring a calculator to it, and this is why, so that you don't have to do this math in your head. But 35,000 divided by 28 is 1250, so that's our F1 for the front tube. What about F2? The only thing that's going to change here, C is going to stay the same, L is going to stay the same, the 4 is not changing. What's going to change is this n, so it's going to go from 1 to 2. So 2 times 2 minus 1, it's not 1, it's 3, right? 3. I'm better at counting for my kid than I am for counting for you guys. Sorry about that. Anyways, this is going to be 3, but what's fun about this is that because none of this other stuff is changing, the only thing that is different is this 3 at the front of the whole equation. This amounts to 1250. It's going to amount to 1250 over here too, and the only change is that you're going to multiply that whole value by 3. So you can basically say, oh, okay, if this is changing, then I can just take this value, multiply it by 3. What do I get? 3750. You might be able to do that one in your head. You might not. It doesn't matter. It will still save you a step even if you're trying to work this out with a calculator. And then class, if I want to calculate the third formant frequency for this front tube, then I'd be going to the scenario where n equals 3, right? So what does this term equal? 2 times 3 minus 1, that's 5. So now I can just take this humdinger and multiply it by 5, right? I don't really have to walk through all these other steps if I don't want to. You can if you do want to, and just if you want to make sure you understand it. You're going to wind up in the same place if you do it right. So this is going to be 5 times 1250, and that will be 6,250 hertz. I asked you in this example at the beginning to say, let's calculate the first 5 formant frequencies for this sort of articulatory configuration. I'm going to calculate the first 3 formants for each of the tubes individually. Then I'll get 6. I'm doing better with that. And so hopefully the lowest 5 formant frequencies will be in that collection of 6. If they're not, we could keep going. It's not that hard to say, well, the next one is like 7 times 1250, so on and so forth. Okay, but we have 3 formants for the front tube. So let's move on to the back tube and see what we get. We're going to do math the same way. We're still using the same equation for this. Instead, the only difference is going to be the length of the back tube is 10.5 centimeters. So this term on the bottom is going to change for our first calculation. Looking at the first formant of the back tube, it's going to be 35,000 divided by 4 times 10.5. Remember, this term reduces to 1 in this case because n equals 1. What does this equal? It's 35,000 divided by 42. You could plop that into your calculator and figure out what it tells you. It should tell you something like 833.33333 hertz. So that's our first formant for the back tube. Our second formant, here's what the math looks like. The only thing that's going to change is that this term is going to be equal to 3. So we can multiply this guy by 3. You might see this already, but that's going to give us a nice round number of 2,500 hertz. So isn't that convenient? It's almost like somebody had in mind that we ought to make the math relatively easy for this before that person set up this example. Thank you, person, whoever you are. Okay, so for this last format, all we need to do is change n to 3. This whole term will wind up being 5. So that means we can multiply this by 5. And that will be equal to 4,166.66666, so on and so forth, hertz. So we've got our lowest 3 formant frequencies for this tube. Now we have to put them together, which we'll do on this slide. So our front tube resonances were these 3 values, 1250, 3750, 6250. For the back tube, we got 833, 2500, and 4133. Did I screw that up? Yeah. I think it's more like this. We'll pretend this part of the video didn't happen, or we can acknowledge that it did and also admit that everybody makes mistakes even when they're recording themselves. So F3 for the, oh man, I thought I had this all set up. Boy, this is the back tube. No wonder I'm making these mistakes. All right, so here we go. Here's our first 3 front tube resonances. Here's our first 3 back tube resonances. How do they fit together in the whole shebang? Basically, we look at this collection of 6, and our first formant frequency is going to be the lowest formant frequency out of all 6 of these, which is this one, right? It's the smallest number. So that's my first formant. And then I just walk up the scale looking for the next highest frequency, which will be 1250. And then after that, my third highest is this one, 2500. My fourth highest is this one, 3750. And then the fifth one is right after that. I still screwed it up. Man. Never hire an amateur, huh? Anyways, that's what you get. It doesn't matter where they come from. This particular example, they're going to be alternating, at least for now, as we go up to the 5th formant. So back tube, front tube, back tube, front tube, back tube, so on and so forth. That doesn't have to be the case. Whichever one is next on the scale as you go up the frequency scale, that's going to be your next formant. Yeah, but hopefully that makes sense. And then also don't get hung up on the fact that I'm calling this the 2nd formant for the back tube. It's going to be the 3rd formant for the whole vowel, right? Because it has to kind of compete with these other formants from the front tube. Yeah. You might be expected to do the math for this sort of thing on an exam that you may or may not take in this class. So if you're not comfortable with this, I recommend going through this whole thing again, or maybe even changing the values for the lengths of the tubes, just so you can get yourself to a point where you're confident in walking through the arithmetic for this. But otherwise, I'm not going to say anything about it now because I think this adequately exemplifies how this process, this mathematical algorithm, is supposed to be used to derive these expected formant frequencies for a 2-tube model. Okay, that was a mouthful. I'm going to move on. Okay, here's something else that we have to consider when we're actually producing vowels in this model. So the lowest resonant frequency of an open tube of length 17.5 centimeters is 500 hertz. That's what we get for the vowel schwa, as we've talked about before. If we just open up our mouths and phonate, and if you have a vocal tract about the length of mine, you get and that F1 will wind up being 500 hertz. In the tube model, how do you get resonant frequencies lower than 500 hertz? How does that work? Because remember, we have this tube of 17.5 centimeters in the 2-tube model. We're making 2 shorter tubes out of that longer tube. So the longest tube out of those 2 tubes is one supposed to give us F1, right? But we don't make the whole tube longer, right? To get a formant frequency lower than 500 hertz, we'd expect to have a tube that's longer than 17.5 centimeters. So we're not doing that, but we can get F1s that are lower than 500 hertz. We know that from the way we draw the vowel space, right? There's lots of high vowels up there, right? How do we get those low F1s? I don't think we're extending our vocal tract to be longer than it is for a schwa. So what happens instead? I'm actually going to pause here and let you think about it for a second. If you come up with a good answer, let me know. If not, you can always watch the next video. So I'll see you then.